Welcome to Orbit into Sleep. Tonight's video is called Relaxing James Webb Space Telescope, Facts to Fall Asleep To. Hello and welcome back. If this is your first time here, I am so glad you found us. Get yourself comfortable, pull your blanket up a little, let your head settle gently into the pillow. Tonight, we are going on the most peaceful journey imaginable, all the way to the edge of the known universe. And the best part? You don't have to move a single inch. Before we begin, if you are enjoying what we do here at Orbit into Sleep, it would mean so much if you took a moment to like this video and subscribe to the channel. It is such a simple thing, but it genuinely helps other people who are lying in their beds right now, staring at the ceiling, find their way here. So if you can, please do. We would love to have them. And while you are in a generous mood, we would absolutely love to know in the comments, roughly, how many hours of sleep do you normally get per night? Are you someone who drifts off easily and wakes up refreshed? Or are you one of our loyal night owls, still awake at 2 a.m, hoping tonight might be different? There is no judgment here, only warmth. Drop your number in the comments whenever you get a chance. Now, let us talk about the James Webb Space Telescope. This is a machine so extraordinary, so impossibly ambitious, that thousands of scientists and engineers spent over 30 years of their lives building it. And on Christmas Day 2021, it was launched into space on a journey to a point 1.5 million kilometers from Earth, where it would spend its days staring into the very beginning of time. Tonight, we are going to float gently through what it is, how it works, what it has seen, and what those things mean for how we understand the universe we live in. There is nothing you need to do, nothing to remember, nothing to worry about. Just listen, breathe, and let your mind drift slowly outward into the deep, quiet dark between the stars, drifting to the edge of the solar system. Let's begin right at the very start, before there were any images. Before there were any discoveries, there was simply a question that had been sitting quietly in the minds of astronomers for a very long time. What did the universe look like when it was young? Not just young in the way that we think of ancient things here on Earth, not hundreds of years old, or thousands, or even millions, but young in the deepest possible sense, young as in only a few 100 million years old, in a universe that is now 13.8 billion years old. That is barely a breath, a single slow exhale at the very beginning of everything. To answer that question, scientists needed a telescope unlike anything that had ever been built. And so, in September of 1989, a group of astronomers gathered at the Space Telescope Science Institute in Baltimore, Maryland, and began to dream one up. They called the meeting a workshop, but really, it was the beginning of something that would take 3 decades to complete. They were asking themselves what should come after the Hubble Space Telescope. What could humanity build next if it dared to try? The answer they eventually arrived at was the James Webb Space Telescope. And it was, from the very beginning, one of the most ambitious engineering projects in human history. Now, before we talk about the telescope itself, it helps to understand something about light. because the James Webb was not built to see the same things your eyes can see. It was built to see something altogether different, something invisible, something felt rather than seen. It was built to see infrared light. You have experienced infrared light before, even if you didn't know it. When you hold your hands near a warm mug of tea and you feel that gentle heat radiating outward before you even touch it, that is infrared radiation reaching your skin. It is light, but it is light that sits just below the threshold of what our eyes can detect. And here is the thing about the universe. The most distant objects in it, the things that formed when everything was young and new and just beginning to take shape, their light has been traveling toward us for so long, across such unimaginable distances, that by the time it reaches us, it has been stretched, pulled thin and long by the expansion of the universe itself, like a sound that drops in pitch as it moves away from you. That stretching shifts visible light down into the infrared, which means that if you want to see the very first stars and galaxies, you cannot use an ordinary telescope that sees only visible light. You need a telescope that can see in the infrared. And that, in its simplest form, is why the James Webb Space Telescope exists. The telescope was launched on Christmas Day, 2021, from a place called the Guyana Space Center in Kourou, French Guiana. It lifted off aboard an Ariane 5 rocket provided by the European Space Agency. And it was a Christmas gift to every human being who has ever looked up at the night sky and wondered what was out there. Its destination was a location in space known as the Second Lagrange Point, or L2. This is a gravitational sweet spot, a place where the combined pull of the sun and the Earth balance each other perfectly, allowing an object to sit in a kind of stable orbit while always keeping the same face toward the inner solar system. It sits 1.5 million kilometers from Earth, which sounds like an enormous distance, and it is. But in the context of a universe 13.8 billion light years across, it is barely a step outside the front door. The reason the telescope needed to go there, so far from Earth, relates to something deeply important about how it works. Because in order to detect the incredibly faint infrared glow of galaxies that existed 13 billion years ago, the telescope itself must be cold, almost unimaginably cold. Think about this gently for a moment. Any object that has warmth to it, any object above the temperature of absolute zero, emits its own infrared radiation. That includes the telescope. That includes its mirrors. That includes the whole spacecraft. If the James Webb were sitting at room temperature, its own gentle warmth would completely overwhelm the tiny whispers of light it is trying to detect from the edge of the universe. And so it had to be cold, not just cold the way a winter morning is cold, or even cold the way the surface of the moon gets cold at night, but truly, profoundly, astonishingly cold. The telescope's mirrors needed to be kept at around 37 Kelvin, which is minus 236 degrees Celsius. That is colder than almost anywhere in our solar system. To achieve that, the James Webb carries something extraordinary with it, a sun shield. And not just any sun shield. A 5-layered structure the size of a tennis court, folded carefully and precisely into the nose of the rocket for launch, and then unfolded in space like the most delicate origami you could imagine. Each of those 5 layers is made from a material called Captain, a kind of high-performance film coated with aluminum. The layers are separated by gaps that allow heat to radiate away between them. The result is breathtaking. On the side of the sun shield facing the sun, temperatures reach around 85 degrees Celsius, warm enough to boil water. But on the other side, where the telescope quietly waits in the shade, it is minus 233 degrees Celsius. That difference across just a few meters of layered film is one of the greatest feats of passive thermal engineering ever achieved. Now, the telescope did not simply drift to its destination fully formed. The journey to L2 took about a month, and during that time the telescope had to unfold itself. Step by step, mechanism by mechanism, it deployed its sun shield, it unfolded its secondary mirror, and it opened up the great golden flower of its primary mirror. That primary mirror is perhaps the most iconic thing about the James Webb. It is 6.5 meters across, made up of 18 hexagonal segments, each one coated in a layer of gold just 100 nanometers thick. In total, the gold used to coat the entire mirror weighs approximately 48 grams, roughly the same as a golf ball. Gold was chosen not for luxury, but for science. Gold reflects infrared light with extraordinary efficiency, somewhere between 98 and 99%. Aluminum or silver, the kinds of coatings used on other telescopes, can only manage 85 to 95%. In the business of collecting ancient light from billions of light years away, every fraction of a percent matters enormously. The whole mirror, all 18 segments together, has a collecting area of 25.4 square meters. That is more than 6 times the collecting area of the Hubble Space Telescope. When it comes to gathering light, size is almost everything, and the James Webb is very, very large. But there was a problem. A mirror 6.5 meters across cannot fit inside a rocket, not as a single solid piece, and so it had to fold. The 18 segments were designed to fold inward like the petals of a flower closing for the night, nestled safely within the rocket's protective shell. And once in space, with extraordinary precision, they had to unfold and align themselves to work as a single, unified mirror. The alignment alone took months. Each segment is mounted on 7 tiny actuators, small mechanical arms that can nudge the mirror by the tiniest amounts. Engineers on the ground sent commands across 1.5 million kilometers of empty space, gently adjusting each segment until all 18 were working together as one. The final wavefront error, which is the measure of how perfectly the mirrors align, came in at just 65 nanometers, far better than required. It is worth pausing on that number for a moment. 65 nanometers. A human hair is roughly 80,000 nanometers wide. The mirror alignment of the James Webb Space Telescope is accurate to less than 1,000th the width of a single strand of your hair. There is something deeply calming about that level of care, about the idea that thousands of people spent years thinking about how to be that precise, not for profit, not for power, but simply to see further, to know more, to understand where we come from. And now it sits out there at L2, cold and still and golden in the dark, waiting patiently for light that has been traveling toward it for longer than the Earth has existed. Just floating, listening, watching. And so can you. Just float, just listen, let yourself be still. There is nowhere else to be tonight. A golden mirror and the instruments behind it. So we have our telescope, cold, golden, perfectly aligned, sitting quietly at its post 1.5 million kilometers from home. But a mirror on its own, however beautiful, is just a mirror. What transforms the James Webb from an engineering marvel into a scientific revolution is what sits behind it. The instruments, the eyes within the eye. The James Webb carries 4 main scientific instruments, and together they cover a range of light from the edge of what we can just barely see with our eyes, all the way down into the deep mid-infrared. Each one was built by a different team in a different part of the world, and each one does something slightly different. But they all share the same extraordinary purpose: to take the light gathered by that great golden mirror and turn it into knowledge. Let us start with the one you have probably seen the most results from, the near-infrared camera known as NIRCam. NIRCam is the telescope's primary imager. It is the instrument responsible for those breathtaking images that have been appearing on the front pages of newspapers and filling social media feeds since the summer of 2022. It sees light in wavelengths from 0.6 to 5 microns, just beyond the edge of visible red light, stretching down into the near-infrared. It was developed by the University of Arizona in partnership with Lockheed Martin, and it is equipped with something called coronagraphs. These are tiny masks that can block out the blinding light of a star, allowing the camera to look for much fainter things in its immediate neighborhood. Planets, for instance, debris disks, the faint structure of forming solar systems. But NIRCam does something else too, something that might surprise you. It serves as the telescope's mirror alignment tool. Throughout the mission, NIRCam takes careful images of bright stars and analyses the shape of their light with extraordinary precision. If the mirror segments have drifted even slightly out of alignment, NIRCam is the instrument that detects it, and its data is used to guide the actuators back into position. It is at once an artist and an engineer. Now, just take a slow breath for a moment. Feel the weight of yourself against the mattress. You don't need to hold any of this tightly. Just let it wash gently over you, like light falling softly on still water. The second instrument is called NIR-SPEC, the near-infrared spectrograph. And while NIRCam takes pictures, NIR-SPEC does something rather different. It takes spectra. It spreads light out, the way a prism splits sunlight into a rainbow, and analyses the individual wavelengths within it. From that analysis, scientists can determine the chemical composition of a galaxy, its temperature, its age, how fast it is moving, and in which direction. A spectrum is like a fingerprint. no two objects produce exactly the same one. NIR spec was provided by the European Space Agency, and it contains one of the most remarkable pieces of technology ever sent into space. It is called the Microshutter Array. Picture a grid containing 250,000 tiny windows, each one about the width of a human hair across, each one capable of being individually opened or closed on command from the ground. When astronomers want to study a particular group of galaxies, they program the shutters to open only in the positions of those specific objects, while keeping all the surrounding shutters closed. The light from each chosen galaxy passes through its own tiny window and is captured for analysis. In a single observation, NIRSpec can study more than 100 objects simultaneously. In a universe so vast that every patch of sky contains thousands of galaxies, this ability to multitask is not just convenient, it is essential. The third instrument is called MIRI, the mid-infrared instrument, and MIRI is in a class of its own. While the other instruments work in the near-infrared, MIRI reaches further, seeing wavelengths from 5 all the way out to 28.8 microns. This is deep mid-infrared territory, the kind of light emitted by cooler objects, by thick dust clouds, by the most distant and most red-shifted galaxies, by planetary debris disks that might one day form new worlds. To see at these wavelengths, MIRI cannot simply be cold in the way the rest of the telescope is cold. It has to be colder still, much colder. While the telescope's mirrors sit at around 37 Kelvin, MIRI's detectors need to be kept at just 6.7 Kelvin, that is minus 266 degrees Celsius, within a whisker of the coldest temperature the universe allows. To achieve this, MIRI carries its own dedicated cooling system, a 4-stage hybrid cryocooler using a combination of pulse tube cooling and something called the Joule-Thomson effect, where a gas is expanded rapidly to shed heat. The compressor that drives this system has 2 tiny pistons that move in opposite directions 30 times per second, balanced so precisely against each other that they cancel out almost all vibration. Because even the tiniest tremor at those levels of sensitivity could blur an image. The result is that MIRI's detectors sit at a temperature so cold it is difficult to even imagine, and from that extraordinary stillness they capture light that has been traveling across the universe for 13 billion years. The fourth instrument is a joint contribution from the Canadian Space Agency. It has 2 parts that work together, known together as FGS-NIRISS, the Fine Guidance Sensor, and the Near-Infrared Imager and Slitless Spectrograph. The Fine Guidance Sensor is not a science instrument in the traditional sense. Its job is to keep the telescope pointed with absolute precision. It does this by locking onto guide stars and monitoring them continuously, making tiny corrections to ensure the telescope never drifts. Its precision is remarkable. It can hold the telescope steady to within 7/1000ths of an arc second. To give you a sense of what that means, it is the equivalent of seeing the thickness of a single human hair from a kilometer away and never losing focus on it. NIRISS, its companion, provides a set of specialized capabilities that complement the other instruments. One of its most elegant modes is called aperture masking interferometry, which turns the telescope into a kind of simulated array, allowing it to achieve even higher resolution for very bright, closely spaced objects. It is also particularly well suited to studying the atmospheres of exoplanets as they pass in front of their host stars, a technique called transmission spectroscopy. Together, these four instruments give the James Webb a range and sensitivity that no single telescope has ever possessed before. But what makes them even more remarkable is where they sit. They are housed together inside something called the Integrated Science Instrument Module, or ISIM. This is a precisely engineered structure mounted behind the primary mirror, kept at temperatures between 32 and 40 Kelvin, insulated from even the tiny warmth of the spacecraft's electronics. The ISIM is essentially a cold, dark room at the heart of one of the most complex machines ever built, containing 4 extraordinary sets of eyes, each one designed to see something slightly different about the same ancient light. And there is something quietly wonderful about that image, isn't there? A cold, dark room full of careful instruments, waiting patiently in the silence between the stars, listening for whispers from the beginning of time, much like you, perhaps, lying quietly in the dark, letting the world outside slow down, letting the thoughts that felt so urgent just an hour ago begin to soften and drift. You don't need to hold on to anything tonight. The universe has been here for 13.8 billion years. It will still be here in the morning. Just rest. Let yourself be warm and still and safe. And let the quiet do its work. The first light and what it showed us. On the 12th of July, 2022, something happened that felt, to many people who were watching, like a moment that would be remembered for a very long time. NASA released the first science-quality images from the James Webb Space Telescope. The first image was a deep field, a patch of sky so small that if you held a grain of sand at arm's length, it would cover it entirely. And in that tiny patch of sky, the James Webb found thousands of galaxies, some of them close in cosmic terms, some of them extraordinarily far away, their light having traveled for more than 13 billion years to reach the mirror. The galaxy cluster at the center of the image is called SMACS 0723. It sits about 4.6 billion light-years from Earth. And it is doing something that the James Webb was designed to take full advantage of, something called gravitational lensing. Here is how that works. And it is one of those ideas that rewards a slow and gentle turning over in the mind. Einstein's theory of general relativity tells us that mass bends space, not metaphorically, literally. A massive object, a star, a planet, a galaxy cluster, warps the fabric of space-time around it the way a heavy ball warps a stretched sheet of rubber. And when light travels through that warped space, it bends too. It follows the curve. When there is an enormous concentration of mass between us and something even further away, that mass can act like a lens. It bends and focuses and magnifies the light from objects behind it, allowing us to see things that would otherwise be far too faint to detect. The universe, in a sense, is lending us its own gravity as a telescope. In the SMACS 0723 image, the galaxy cluster itself is acting as one of these natural lenses. Behind it, the James Webb can see galaxies from more than 13 billion years ago, their shapes stretched into long, graceful arcs by the lensing effect, like the reflections of distant lights in a curved mirror. What astronomers noticed immediately was that those background galaxies were not the sparse, shapeless smudges that earlier models had predicted. They were structured. Some of them appeared surprisingly mature, surprisingly well organized, for objects that existed when the universe was less than 1 billion years old. This was the first hint that the James Webb was going to challenge some long-held ideas about how galaxies form. But before we follow that thread into deeper waters, let us pause and visit somewhere a little closer to home, somewhere in our own galaxy, a place of extraordinary beauty, the Carina Nebula. The image the James Webb took of the Carina Nebula was released on the same day as the Deep Field, and it produced a very different kind of wonder. Where the Deep Field inspired awe at scale, at distance, at time, the Carina image inspired something more immediate, something almost tender. The image shows what astronomers call the cosmic cliffs, a towering landscape of gas and dust rising in great jagged peaks and valleys, backlit by the fierce radiation of young hot stars. It looks, at first glance, almost like a mountain range at sunset, pale and golden at the peaks, deepening into rich blues and purples in the valleys below. But those cliffs are not mountains. Each one is taller than our entire solar system is wide. And what the James Webb was seeing, hidden within those dense clouds of gas and dust, was something that no telescope had ever been able to see clearly before: the actual process of stars being born. In the near-infrared light that the James Webb sees so well, the thick dust that normally hides these stellar nurseries becomes transparent. And through that transparency, for the first time, astronomers could see individual young stars emerging from their dusty cocoons. Jets of material shooting outward from newborn stars, hundreds of billions of kilometers long, punching through the surrounding gas like needles of light. Take a moment with that image if you can. A newborn star, something that will burn for billions of years, possibly warming planets, possibly nurturing life, just beginning, just taking its first breath of nuclear fire. There is something about the birth of a star, seen this clearly for the first time, that feels unexpectedly moving. Now, the Carina image and the Deep Field were just the beginning. Over the months and years that followed, the James Webb kept sending back data, and the data kept doing the same thing over and over again. It kept surprising people. One of the most persistent surprises was the discovery of galaxies that seemed far too mature for their age. Under the standard model of cosmology, which is called lambda CDM, galaxies are expected to grow slowly over billions of years through a process of gradual merging and accretion. Small things come together to make larger things. Larger things merge to make even larger things. It takes time, a great deal of time. But the James Webb was finding galaxies in the very early universe. Galaxies from just 300 to 500 million years after the Big Bang that already looked old, already looked structured and massive and chemically complex in ways that the models said should not be possible yet. It was as if you found a photograph of someone taken when they were supposedly only a few weeks old, and they were already fully grown. Astronomers began to call these the impossible early galaxies, and while nobody was ready to throw out the standard model entirely, there was a growing sense that something needed to be adjusted, something was being missed. Then, in early 2025, came a discovery that pushed the boundary of the observable universe further than it had ever been pushed before. A galaxy called MOM-Z14. The Z in that name refers to redshift. The number 14.44 refers to how much its light has been stretched on the journey to us. To give you a sense of the scale, seeing a galaxy at redshift 14.44 means you are seeing it as it was just 280 million years after the Big Bang. The universe was 2% of its current age. The Milky Way did not yet exist. The Sun did not yet exist. The Earth would not exist for another 4.5 billion years. And yet there was MOM-Z14 already blazing away, already around 100 times brighter than the theoretical models predicted anything should be at that epoch, already showing signs of nitrogen in its spectrum, which is an element that takes multiple generations of stars to produce in significant quantities. Multiple generations of stars. In a universe that was only 280 million years old. The implications of that are quietly staggering. If you need several generations of stars to produce the chemical signatures being detected, and those stars each live and die over millions of years, then star formation must have begun extraordinarily quickly after the Big Bang, far more quickly than anyone expected. The universe, it seems, did not ease gently into existence. It hit the ground running. And then there was the Big Wheel, discovered in 2024 almost by accident while astronomers were studying something else entirely. The Big Wheel is a giant spiral disk galaxy that existed just 2 billion years after the Big Bang. It has an optical radius of roughly 33,000 light years. Its disk rotates at 300 kilometers per second. In size and structure and mass, it rivals our own Milky Way. The Milky Way took most of the age of the universe to become what it is. The Big Wheel, according to every simulation astronomers have ever run, should not have been possible at that age. No current model predicted anything like it could exist so early. And yet there it is. There is something almost comforting about this, if you let yourself feel it. The universe is bigger and more complex and more surprising than our best theories have accounted for. The map is not the territory. The models are not the reality. And every time we build a better instrument and look more carefully, we find that reality is richer than we imagined. We do not have all the answers. We may never have all the answers. but the questions themselves are so beautiful, and the looking is so worthwhile. And right now, all you need to do is breathe, and let that be enough. The universe has been surprising us for as long as we have been watching it. It will keep surprising us long after tonight, long after this moment, long after any of us are here to watch. And that, in its own quiet way, is a very peaceful thought. A gentle moment before we continue. Before we drift into our next chapter, I just wanted to take a quiet moment to mention something. If you are here listening to this, there is a good chance that sleep does not always come easily for you, and you are very much not alone in that. So many people struggle in so many different ways to find that soft and gentle surrender into rest. If you are looking for a little extra help, I do keep our video description updated from time to time with things that I have come across that might be worth exploring. Whether that is something to read, something to listen to, or something small that might just make bedtime feel a little more peaceful. Nothing dramatic, nothing pushy, just gentle suggestions, there if you want them. Have a look when you get a chance. No rush, no pressure at all. Right, let us get back to the stars, little red dots, and the mystery of the first black holes. There is something rather lovely about the fact that some of the most significant scientific discoveries of recent years were given the most unassuming of names. Little red dots. It sounds like something you might find in a children's book. And yet these tiny, compact, intensely crimson specks of light scattered across the deep field images of the James Webb Space Telescope have sent theoretical physicists into a quiet frenzy because nobody is entirely sure what they are. Let us settle in and think about this gently together. When the James Webb began returning its deep field images, astronomers cataloging the data started noticing something odd. Scattered among the ancient galaxies, there were objects that were very small, point-like, almost, like stars rather than galaxies. But their light was deeply, unusually red, and their spectra, the chemical fingerprints of their light, were strange in ways that did not fit neatly into any existing category. These objects appeared in the early universe, when it was less than 1 billion years old, and despite being extraordinarily compact, they were remarkably bright. Brighter in many cases than they had any right to be. The leading theory, the one that most astronomers have cautiously gathered around, is that many of these little red dots are active galactic nuclei, which is a somewhat formal way of saying that at their hearts, there is a supermassive black hole, and that black hole is feeding. Now, black holes feeding is not itself unusual. Most large galaxies, including our own Milky Way, have supermassive black holes at their centers. When material falls into one of these black holes, it does not simply vanish quietly. It forms a swirling disk of superheated gas and dust around the black hole, spinning faster and faster, heating up to extraordinary temperatures and blazing with intense radiation. These are called accretion disks. And when an accretion disk is active and energetic, it can outshine the entire surrounding galaxy. What makes the little red dots puzzling is not the presence of these active black holes. It is their size. They are far more massive than they should be, given how young the universe was when they existed. Under the standard model of black hole formation, supermassive black holes grow slowly over billions of years, fed by the gradual accumulation of stars and gas. But the black holes implied by the little red dots are enormous already in a universe that had barely begun. Some of them appear to contain black holes hundreds of millions of times the mass of our sun. In a universe only a few 100 million years old, the maths simply does not work if you assume black holes form the way we thought they did. And so theorists have been reaching for new explanations. One of the most intriguing is the idea of direct collapse. Rather than forming from the remnants of individual stars, perhaps the first supermassive black holes form directly from vast collapsing clouds of gas, skipping the stellar stage entirely, a whole cloud of hydrogen, tens of thousands of times the mass of the sun, collapsing directly into a black hole in a single catastrophic event. It is a dramatic idea. And the little red dots may be the first observational evidence that something like this actually happened. But there is another theory, stranger still, that has been gathering attention in the past year or so. And it involves a class of object that, until very recently, existed only in the pages of theoretical papers: the black hole star. The idea goes something like this. Imagine a supermassive black hole, already enormous, surrounded not by a thin accretion disk, but by an extraordinarily thick, dense cocoon of hydrogen gas, so thick, so opaque, that the fierce radiation of the accreting black hole cannot escape outward in the usual way. Instead, it is absorbed and re-emitted by the surrounding gas, which puffs up into a vast, diffuse sphere, hot on the inside, cooler at the surface, glowing in the infrared. From the outside, this object would look something like a star, a very large, very puffy, quite cool star. But it would be powered not by nuclear fusion, the way a real star is powered, but by a black hole consuming matter at its center. These objects, if they exist, would be unlike anything previously identified in the universe. Not a galaxy, not a star, not a standard quasar, something in between, something new. One of the candidate objects for this classification was given the name the Cliff. It sits at a redshift of 3.55, meaning we see it as it was roughly 11.5 billion years ago. Its spectrum fits the black hole star model with uncomfortable precision, and if the interpretation is correct, it represents something remarkable, a missing link in the story of how black holes grew so large so quickly in the early universe. Now, at this point, you might be wondering about something that was mentioned earlier. The little red dots are intensely red and extremely bright, suggesting powerful processes at work. You might expect them to blaze in X-rays. Active galactic nuclei, when we observe them in the nearby universe, typically emit strongly in X-rays, the product of all that violent energy being released. But the little red dots are almost invisible in X-rays. Despite all the spectroscopic evidence that something energetic is happening inside them, they are remarkably quiet at high energies. This is one of the reasons some astronomers have held back from fully committing to the black hole accretion explanation. The X-ray silence is a puzzle within a puzzle, and the black hole star model actually offers an elegant explanation for it. If the black hole is buried so deeply within its thick cocoon of gas, that cocoon would absorb much of the high-energy radiation before it could escape. The X-rays would be swallowed up before they ever reached us. And what we would see instead is the softer, redder, gentler glow of the surrounding gas. There is something almost poetic about that idea. The most violent process in the universe, a black hole consuming matter with ferocious energy, hidden behind a soft and quiet exterior, appearing to the outside universe as nothing more threatening than a warm, diffuse glow. Things are not always what they appear to be, and out there in the dark, ancient universe, in a time before the Earth existed, before the Sun existed, before our entire galaxy had taken its present shape, these strange hybrid objects may have been quietly growing, accumulating mass, building toward the supermassive black holes that would one day anchor entire galaxies, the seeds of something vast and long-lasting, wrapped in a cloak of soft red light. The James Webb Space Telescope was not specifically designed to find any of this. It was designed to look further and more clearly than anything before it. And in doing so, it found things that nobody anticipated. Objects that do not fit the existing categories. Phenomena that require new frameworks to understand. This is, in many ways, the most exciting thing that can happen in science. Not the confirmation of what was expected, but the discovery of what was not. And there is a gentleness in that thought, too, if you let it settle. Not everything has to be understood immediately. Not everything has to be classified and sorted and explained tonight. Some mysteries are allowed to remain open for a while, to sit in the mind like a slow, quiet question, without urgency, without pressure. The little red dots have been sitting out there for more than 12 billion years. They waited that long to be found. They can wait a little longer to be fully understood. And you, lying there in the quiet dark, do not need to solve anything tonight either. Just let yourself be here, warm and still and unhurried. The questions will keep, the universe will keep, and you can rest. Dark stars and the oldest light. There is a particular kind of wonder that comes from imagining the very first stars. Not stars like our sun, which formed nearly 5 billion years ago in a universe already rich with complexity, but the very first ones, the ones that ignited in the darkness when the universe was only a few 100 million years old, when there was no light anywhere, and then, slowly, there was. Astronomers call this period the cosmic dawn, and it is one of the things the James Webb Space Telescope was most specifically designed to illuminate. Before the first stars formed, the universe was a very different place to the one we know. It was filled almost entirely with hydrogen and helium, the two simplest elements produced in the first few minutes after the Big Bang. There were no heavier elements yet. No carbon, no oxygen, no iron, no gold. Those would come later, forged in the hearts of stars and scattered by their deaths. But in the beginning, there was only the simplest chemistry, drifting in vast dark clouds, slowly cooling, slowly gathering under the pull of gravity. And then something ignited. The first generation of stars are known as population 3 stars. We have never directly observed one. They formed too long ago in a universe too young and too far away for any previous telescope to see. But we can infer what they must have been like. Made entirely of hydrogen and helium, with none of the heavier elements that influence how stars form today. They were likely enormous, far larger than most stars that form now. Some theoretical models suggest they could have been hundreds of times the mass of our Sun. They would have burned brilliantly and briefly, living fast and dying young, seeding the universe with the first traces of heavier elements when they exploded as supernovae. The James Webb has been peering into this era, looking for the signatures of these first stars. And what it has found is, as so often, more surprising than expected. Among the earliest, most distant objects detected by the telescope, there are several that have caught the attention of theorists in a particularly striking way. These objects, including ones known by the somewhat unglamorous designations JADES-GS-Z13-0 and JADES-GS-Z12-0, have spectra and brightnesses that do not quite fit the profile of ordinary early galaxies. They are too large, too luminous, too diffuse, and they hint at something that, until recently, was considered purely theoretical. Dark stars. Not dark in the sense of being invisible, dark in the sense of what powers them. The theory of dark stars was first proposed in 2007, and it begins with a question about dark matter. We know that dark matter exists because we can see its gravitational effects throughout the universe. It bends light. It holds galaxies together. It shapes the large-scale structure of everything we can observe, but we do not know what it is made of. One leading candidate is a class of particles called weakly interacting massive particles, or WIMPs. WIMPs have a fascinating theoretical property. If they are their own antiparticles, then when two of them collide, they annihilate each other, and that annihilation releases energy. Now, in the very early universe, the densest concentrations of dark matter were the seeds around which the first hydrogen clouds gathered and collapsed. If WIMPs were present in large enough numbers at the center of these collapsing clouds, their annihilation could release enough energy to heat the cloud from within, to slow its collapse, to hold it in a kind of warm, bloated equilibrium, neither fully collapsing nor dispersing. The result would be an object unlike any star that exists today, not powered by nuclear fusion at its core, the way our Sun is powered, but by the annihilation of dark matter particles throughout its volume. An object that could be absolutely enormous, perhaps as wide as 10 times the distance from the Earth to the Sun, with a relatively cool surface temperature of around 10,000 Kelvin and a luminosity billions of times greater than our Sun. A dark star. The reason this theory has gained renewed attention is that objects like JADES-GS-Z 13-0 fit its predictions remarkably well. They are bright enough to be seen at redshifts above 13. They are diffuse and extended rather than compact. And crucially, some of them show a spectral feature involving helium that is characteristic of the particular conditions a dark star would produce. There is something almost dreamlike about this idea. Stars powered by dark matter, objects that glow not with the fire of nuclear fusion, but with the quiet energy of matter and antimatter canceling each other out. Deep in the dark heart of a primordial cloud, enormous, puffy, warm, sitting at the edge of the observable universe, in a time before anything we would recognize had yet come to exist. If dark stars are real, they add yet another layer of complexity to the story of how the universe went from the simplicity of the Big Bang to the extraordinary richness of what exists today. They may have been the stepping stones between the first dark matter halos and the first supermassive black holes, growing to enormous masses before finally exhausting their dark matter supply and collapsing, seeding the universe with the heavy seeds that would eventually become the black holes at the hearts of galaxies, including perhaps the black hole at the heart of our own Milky Way. Now, the evidence for dark stars is not yet conclusive. The objects that fit the theory could potentially be explained by other means: dense early galaxies, unusual population 3-star clusters, or new configurations of ordinary matter that we have not fully modeled. The helium spectral features that would serve as a definitive smoking gun have been tentatively identified in some objects, but have not yet been confirmed beyond reasonable doubt. This is how science works, of course. Slowly, carefully, with each piece of evidence building on the last. Nobody announces a dark star on the basis of one observation. The confirmation will take time and more data, and the careful cross-checking of independent teams working independently toward the same question. But the fact that these objects exist at all, the fact that the James Webb can see things at redshift 13 and above, things from just a few 100 million years after the Big Bang, is itself extraordinary. Every image, every spectrum, every data point from those distances is a message in a bottle from the very beginning of the universe, sent before the Earth existed, traveling for almost the entire age of everything. And here we are, receiving it. There is a very particular kind of quiet that comes from sitting with a thought like that. The light that the James Webb is capturing right now, in this moment, tonight, as you lie there in the warmth of your bed, left its source more than 13 billion years ago, before our sun ignited, before the solar system coalesced from its spinning disk of gas and dust, before the first single-celled life appeared in Earth's ancient oceans. That light has been traveling through the dark, through the expanding universe, through the vast and empty spaces between galaxy clusters for all of that time. And it arrived at last at a golden mirror, folded carefully into a rocket and launched on Christmas morning and carried by human hands and human minds to a point in space chosen for its stillness. It is one of the most patient journeys imaginable, and perhaps there is something in that patience that speaks to tonight, to this quiet hour, to the way sleep, when it comes, does not come from effort or from urgency, but from letting go, from allowing the stillness to arrive in its own time. The universe has been patient for 13 billion years. You can afford to be patient for a little while longer. Just breathe. Let your thoughts drift like light through the dark. Let them travel wherever they want to go, without urgency, without destination. There is nothing required of you right now. Nothing at all. Just this. Just rest. The tension in the universe and the distance of stars. There is a number that has been quietly causing arguments among astronomers for the better part of a decade. It is called the Hubble constant, and despite its name suggesting something fixed and settled, it has turned out to be one of the most contentious quantities in modern cosmology. The Hubble constant describes how fast the universe is expanding. Specifically, it tells us how quickly galaxies are moving away from us as a function of their distance. The further away a galaxy is, the faster it appears to recede. And the Hubble constant is the number that describes that relationship. It is usually written as a velocity per unit of distance, kilometers per second per megaparsec, a megaparsec being roughly 3.3 million light years, and the currently accepted range of values sits somewhere between 67 and 73 kilometers per second per megaparsec, depending on how you measure it, which sounds like a fairly narrow range, until you realize that the two main methods of measuring it consistently give different answers, and that those different answers have refused, despite years of effort and increasingly precise instruments, to agree with each other. This disagreement has come to be known as the Hubble tension, and it is one of the things the James Webb Space Telescope was hoped to help resolve. Let us start from the beginning, because it helps to understand why this matters. When we want to measure how fast the universe is expanding, we need to know two things about a distant galaxy. We need to know how fast it is moving away from us, which is relatively straightforward to determine from the redshift of its light. And we need to know how far away it actually is, which is considerably harder. Distance in astronomy is not something you can measure directly. You cannot stretch a tape measure across a billion light years. Instead, astronomers have built up what they call the cosmic distance ladder, a series of overlapping techniques, each one calibrated against the one below it, allowing distances to be estimated further and further out into the universe. The lowest rungs of this ladder involve objects whose true brightness we think we know. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. The fainter it appears relative to its true brightness, the further away it is. One of the most important of these objects is a type of star called a Cepheid variable. Cepheid variables pulsate. They brighten and dim in a regular rhythmic cycle, and the period of that cycle, how long it takes to go from bright to dim and back again, is directly related to the star's true luminosity. Measure the period and you know the true brightness. Compare that to the apparent brightness and you have the distance. Cepheid variables have been the backbone of the cosmic distance ladder for over a century, and they are one of the primary tools used by a team called the SH0ES collaboration, led by astronomer Adam Rees, to measure the Hubble constant. Their answer, refined over many years of careful observation, comes in at around 73 kilometers per second per megaparsec. The other main method of measuring the Hubble constant works from completely the opposite direction. Rather than building up from nearby distance measurements, it starts from the very beginning of the universe. From the cosmic microwave background, the faint glow of radiation left over from the Big Bang itself, measured with extraordinary precision by satellites like the Planck Observatory. By analyzing the pattern of tiny temperature fluctuations in the cosmic microwave background, cosmologists can extract a value for the Hubble constant that depends not on any local distance measurements, but on the physics of the early universe. And the answer they get is around 67.4 kilometers per second per megaparsec. 67.4 versus 73.2. A gap of nearly 6 kilometers per second per megaparsec, which in the grand scheme of cosmology is not enormous in absolute terms, but is far larger than the measurement uncertainties of either method. Both teams have checked their work and checked it again, and the discrepancy remains. Stubbornly, uncomfortably. This is the Hubble tension, and it matters because if both measurements are correct, then one of two things must be true. Either there is some systematic error in one or both of the methods, some subtle bias or miscalibration that nobody has yet identified, or the standard model of cosmology is missing something. Some physics that affects the expansion of the universe in ways that the current equations do not account for. The James Webb Space Telescope was seen as a potential referee in this dispute. With its extraordinary resolution and sensitivity in the near-infrared, it could observe Cepheid variables in distant galaxies with far greater precision than Hubble ever could. It could check the measurements, tighten the uncertainties, perhaps identify where the discrepancy was coming from. The results so far have been fascinating and characteristically complicated. The James Webb has confirmed that the Cepheid measurements themselves are sound. The distances derived from Cepheid variables using the James Webb are consistent with those from Hubble, suggesting that the SH0ES team's value of around 73 is not the result of some systematic error in the Cepheid method. But the James Webb has also enabled more precise measurements using other distance indicators. One of these is a method based on stars called JAGB stars, a particular class of carbon-rich giant stars whose brightness can be used as a standard ruler. Another uses the tip of the red giant branch, a very specific brightness threshold that all stars of a certain type reach just before they undergo a dramatic change in their lives. When astronomer Wendy Friedman and her team used these alternative methods with James Webb data, they arrived at a value of around 70.4 kilometers per second per megaparsec, closer to the middle, overlapping, within its uncertainties, with the Planck value from the early universe, which might suggest the tension is easing. That perhaps the discrepancy was always a matter of measurement systematics rather than new physics. Except that Rice and the SH0ES team, also using James Webb data, still find 73. Still find a significant tension with Planck. The different teams are using the same telescope, looking at the same universe, and still arriving at different answers. Not because anyone is making mistakes, but because the problem is genuinely hard, and because the systematic uncertainties in each method are subtle and fiendishly difficult to fully account for. And so the Hubble tension remains. A little softer around the edges, perhaps, a little more nuanced, but unresolved. What this means for cosmology is still being worked out. Some theorists have proposed modifications to the standard model that could explain the discrepancy. Perhaps dark energy, the mysterious force driving the accelerating expansion of the universe, is not the simple constant that Einstein introduced, but something more dynamic, something that has changed over time. If dark energy were stronger in the early universe than it is today, it could affect the early universe measurements in a way that might explain the gap. Others have proposed new forms of matter, or modifications to the behavior of gravity, or exotic early universe physics involving extra relativistic species of particles. The theoretical landscape has become quite colorful, and this is perhaps the most important thing to say about the Hubble tension. It is not a crisis. It is not a reason to panic or to lose faith in our understanding of the universe. It is an invitation, a signal from the data that there may be something new to discover, something that lies just beyond the edge of our current understanding, waiting to be found. The universe has been generous in this regard. Every time we have looked more carefully, we have found more. Every time we have built a better instrument, the sky has rewarded us with surprises. The Hubble tension may be the universe's way of telling us that our model, as good as it is not yet complete. And there is something rather beautiful about that. About living in a time when the universe is still offering us new questions, when the map still has edges, when there are still things to find. It is very late now, wherever you are, and the questions of the universe, as fascinating as they are, do not need to be answered tonight. They have been waiting for billions of years. They will wait a little longer. Let your mind soften around those ideas. The expanding universe, the distance of stars, the quiet argument between two numbers that has been running in conference rooms and telescope domes and late-night emails between scientists for years. It is a gentle kind of mystery, the kind you can hold loosely without urgency. The kind that makes the universe feel alive and interesting rather than finished and explained. And you are alive in it, right now, warm and breathing and safe, and already beginning to drift. Let yourself go the rest of the way. The search for life and the chemistry of the cosmos. Of all the questions that human beings have ever asked, there is perhaps one that sits closest to the heart. Are we alone? It is a question that has been asked around campfires and in temples and in laboratories and in the quiet of sleepless nights for as long as people have been looking up at the stars. And it is a question that the James Webb Space Telescope, though not specifically designed as a life detection instrument, has begun to approach in ways that would have seemed extraordinary just a decade ago. Let us drift into that question gently tonight. The search for life beyond Earth in modern astronomy does not begin with looking for cities or signals or spacecraft. It begins with chemistry, with molecules, with the specific combinations of atoms that, on our world at least, are associated with biological processes. The idea is that life, wherever it exists, must leave chemical traces in the environment around it. And if those traces appear in the atmosphere of a distant planet in concentrations that cannot be easily explained by ordinary chemistry, they might be telling us something. These chemical traces are called biosignatures, and the James Webb Space Telescope, with its extraordinary spectroscopic sensitivity, is the first instrument ever built that can meaningfully search for them in the atmospheres of planets orbiting other stars. The technique it uses is called transmission spectroscopy. When a planet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb different specific wavelengths of light. By comparing the spectrum of the star when the planet is in front of it to the spectrum when the planet is elsewhere, astronomers can identify which wavelengths have been absorbed and from that, which molecules are present. It sounds almost impossibly delicate, and it is. The atmosphere of a planet is a thin sliver of gas wrapped around a ball of rock, filtering a tiny fraction of the light from a star billions of kilometers away. But the James Webb is sensitive enough, just barely, and the results it has already returned are tantalizing. One of the most talked about targets is a planet called K218b. K218b orbits a small red star about 120 light-years from Earth. It is what astronomers call a sub-Neptune, larger than Earth but smaller than Neptune, sitting in the habitable zone of its star, where liquid water could potentially exist on its surface. Some theorists have proposed that K218b might be a Hycean world, a planet covered by a vast, deep ocean beneath a hydrogen-rich atmosphere with conditions that might, in principle, support life. In 2023, the James Webb returned a spectrum of K218b's atmosphere, and within that spectrum, there was a signal, a faint but intriguing hint of a molecule called dimethyl sulfide. Dimethyl sulfide. On Earth, this molecule is produced almost exclusively by living things, specifically by marine algae and microbes in the ocean. It is one of the compounds responsible for that distinctive smell of the sea. And it is considered one of the most promising potential biosignatures because there is no known abiotic process on an Earth-like world that produces it in significant quantities. The initial reports described a 3 sigma confidence detection, which in scientific terms means the signal was strong enough to be worth paying serious attention to, but not yet strong enough to be called a confirmed discovery. A 3 sigma result has roughly a 1 in 1,000 chance of being a statistical fluke, which sounds reassuring until you consider how many spectra are being analyzed and how many opportunities there are for flukes to appear, And then, in 2025, independent teams reanalyzed the data, and the picture became more complicated. The reanalysis suggested that what had appeared to be a biosignature signal might instead be contaminated by what scientists call red noise, a kind of systematic correlated noise in the mid-infrared data that can mimic the appearance of a molecular absorption feature. When this noise component was carefully modeled and removed, the statistical significance of the dimethyl sulfide detection dropped considerably, to the point where the teams concluded there was, as yet, no statistically significant evidence for biosignatures on K218b. This is not a failure of science. This is science working exactly as it should. A tentative signal, examined carefully, tested rigorously, and found to require more evidence before any conclusion can be drawn. The answer, for now, is not yes and not no. It is the most honest answer of all. We do not yet know. And there was a further complication. It emerged that dimethyl sulfide, long assumed to be almost exclusively biological in origin, can actually be produced abiotically. It was detected on a cold, lifeless comet. It can form through photochemistry in hydrogen-rich atmospheres without any need for biology at all, which means that even a confirmed detection of dimethyl sulfide on K218b would not, on its own, be proof of life. It would be a clue, an interesting, exciting, worth following up clue, but not proof. The search for life is like that, full of clues that lead to more questions, full of signals that might mean everything or nothing, full of moments of excitement followed by careful, humbling re-examination. But the search goes on, and the James Webb has opened doors that were previously closed entirely. In a very different corner of the search for life's building blocks, the telescope has been looking not at exoplanets, but at the cold, dark spaces between the stars, the interstellar medium, and there it has found something quietly remarkable. Working alongside radio telescopes, the James Webb has helped detect phosphorus-bearing molecules in a starless core, a cold, dense cloud of gas and dust called PERS 326, which has not yet begun to collapse into a star. And in that cloud, in conditions colder and emptier than almost anything we can imagine on Earth, there are molecules containing phosphorus. Phosphorus is one of the essential elements of life as we know it. It is a key component of DNA and RNA, the molecules that carry genetic information in every living cell on Earth, and finding it in molecular form in the earliest stages of star and planet formation, before any star has even ignited, tells us something important. The raw ingredients of life are present in the universe from the very beginning of the stellar life cycle, before planets form, before any warmth exists to nurture chemistry. The building blocks are already there, waiting. There is something deeply moving about that if you let yourself feel it. The atoms that make up your body, the phosphorus in your DNA, the carbon in your cells, the oxygen in the air you are breathing right now, They were forged in the hearts of stars and scattered by their deaths, and then gathered again across billions of years into clouds, and then into solar systems, and then into planets, and then into oceans, and then into the first fragile cells, and then through an almost incomprehensible chain of events into you. And the James Webb is showing us that this process is not unique to our corner of the galaxy. The same chemistry is happening everywhere, in starless clouds light years across, in the atmospheres of planets orbiting distant suns, in galaxies so remote that the light leaving them has been traveling since before the Earth existed. Life, if it exists beyond Earth, would not be an accident. It would be an expression of chemistry that is written into the fabric of the universe itself. That is not a small thought to carry into sleep. There was one more discovery worth mentioning here, at the gentle edge of the strange. The James Webb detected phosphine gas in the atmosphere of an ancient brown dwarf called Wolf 1130c. Phosphine, a molecule made of one phosphorus atom and 3 hydrogen atoms, has been proposed as a potential biosignature for anaerobic life on rocky planets. Its detection in the atmosphere of Venus a few years ago caused considerable excitement and considerable subsequent debate. On Wolf 1130c, a failed star too small to sustain nuclear fusion, the presence of phosphine is not thought to indicate biology. Instead, it likely reflects the unusual chemistry of a metal-depleted atmosphere where there is insufficient oxygen to bind the phosphorus into other compounds, leaving it free to form phosphine in the hydrogen-rich environment. Unusual, interesting, but probably not alive. And yet the fact that phosphine appears in unexpected places, that the molecules we associate with life keep turning up in corners of the universe where we did not expect them, feels like the universe gently nudging us, reminding us that chemistry is creative, that molecules find each other in the dark, that the universe does not wait for permission before trying something new. We are looking for life out there, and in looking, we keep finding the ingredients scattered everywhere, like a kitchen already stocked and waiting, in world after world after world. Whether anything has yet sat down at that kitchen and started cooking, we do not yet know. But the search is the most human thing imaginable. And the James Webb Space Telescope is the finest instrument we have ever built to conduct it. You are part of a species that built a golden mirror and sent it to the edge of the solar system to look for the chemistry of life in the atmospheres of planets orbiting other suns. Take a moment with that, with what it means to be that kind of creature. Curious, reaching, unwilling to accept the limits of what can be known. And then gently let it go. Let your curiosity rest for tonight. Let your reaching arms fall softly back to your sides. Let the questions float up and away, like breath on a cold morning, dissolving quietly into the dark. You have thought enough for one night. You have wondered enough. Now it is time to simply be. Warm, still, safe, here.